Hello everyone. Have you ever wondered why fireworks burst into beautiful colors with sharp, distinct lines? It's not magic, it's all thanks to atomic spectra. Funny thing, atoms might be tiny, but they put on quite the light show. So, why exactly do atoms emit light? Well, when an electron in an atom jumps from a higher energy level down to a lower one, it releases energy in the form of electromagnetic radiation. This energy comes packaged in little bundles called photons, and the energy of each photon equals Planck's constant times the frequency of the light. Mathematically, energy E equals h multiplied by the Greek letter nu, which stands for frequency. Now, instead of a smooth rainbow like sunlight, these emitted photons create a spectrum full of sharp lines. Each line matches a specific energy difference between two quantized energy levels, so the change in energy, delta E, equals the energy of the initial level minus that of the final level, and that difference is exactly h times nu. What's cooler is that each element shows its own unique line spectrum. The pattern acts like a fingerprint because atoms have their own set of allowed energy levels. Seeing only certain wavelengths appear tells us that energy levels inside atoms aren't continuous, they're quantized. So next time you gaze at neon signs or star glimmers, remember, those bright, sharp lines are electrons jumping down energy ladders and saying hello with photons. Hey curious minds! Let's zero in on hydrogen, the simplest atom but full of fascinating secrets. A Swiss physicist named Rydberg came up with a beautiful formula that summarizes hydrogen's spectral lines, kind of like a master key. This formula reads 1 divided by lambda equals the Rydberg constant for hydrogen multiplied by the quantity open parentheses 1 divided by n1 squared minus 1 divided by n2 squared close parentheses, where n2 is greater than n1. In simpler words, the inverse of the wavelength equals a sub h times the difference between 1 over n1 squared and 1 over n2 squared. Now, what's special about the Balmer series? It shows up in the visible region of light, which means these are the lines we can actually see with our eyes. Balmer series happens when electrons fall from higher levels like n2 equals 3, 4, 5, and so on, down to n1 equals 2. But hydrogen has other series too, Lyman in the ultraviolet, invisible to us, and Passion in the infrared, also beyond visible light. Together, they reveal hydrogen's full electromagnetic spectrum. The Rydberg constant, that magic number, is about 1.097 times 10 to the 7th per meter, found experimentally to slip neatly into the formula for hydrogen-like atoms. Thanks to Rydberg, we can predict where hydrogen's spectral lines fall with impressive accuracy, which is pretty handy whether you're studying stars or lasers. Welcome back. Let's revisit the classic Bohr model, our very first atomic picture that really nailed quantized energy levels. According to Bohr, the allowed energies of an electron and hydrogen are given by energy E sub n equals negative 13.6 electron volts divided by n squared, where n can be 1, 2, 3, and so on. So, the energies are negative, meaning the electron is bound to the nucleus, and as n increases, the energy moves closer to zero, which represents a free electron not bound anymore. Now, when an electron jumps from an initial energy level n sub I to a final level n sub f, the energy of the emitted or absorbed photon equals the difference in these energies, delta E equals E sub nf minus E sub ni, and this is also equal to h times nu, Planck's constant multiplied by the frequency of the photon. This energy difference gives rise to spectral lines you can observe as electrons drop to lower energy levels. Each unique delta E produces a unique frequency or color in the atom's spectrum. So, Bohr's model elegantly explains why spectral lines are discrete, because energy levels are quantized. And remember, the negative sign in energy tells us the electron is held tightly by the nucleus, but as it tends to infinity, that energy approaches zero, meaning the electron escapes completely. It's like energy steps that get closer and closer to freedom. Alright, let's do a quick practice with the Balmer series because seeing the math makes it stick. Suppose an electron in a hydrogen atom falls from energy level N2 equals 3 down to N1 equals 2, and we want to find the wavelength of the light emitted. We start with the Rydberg formula, 1 over lambda equals R sub h multiplied by the difference between 1 over 2 squared minus 1 over 3 squared. Plugging in the numbers, 1 over lambda equals 1.097 times 10 to the 7th per meter times open bracket 1 over 4 minus 1 over 9 close bracket. Calculating the difference inside the bracket gives 5 over 36. So, 1 over lambda equals 1.097 times 10 to the 7th times 5 divided by 36. Crunching the numbers, lambda comes out to about 656.3 nanometers, which you can recognize as the famous red line in the Balmer series of hydrogen spectrum. So, the simple jump from level 3 to level 2 gives us a beautiful deep red. No wonder those neon signs glow so prettily. Let's classify all those spectral lines neatly, because hydrogen has quite a family of series. When electrons transition to a fixed lower energy level N1, we get different spectral series. For example, when N1 equals 1, the transitions form the Lyman series, which appears in the ultraviolet region, too energetic for our eyes to see. For N1 equals 2, you get the Balmer series, the one invisible light we just saw. When N1 equals 3, the Paschen series comes along, showing up in the infrared region. Each series occupies a distinct region in the electromagnetic spectrum because the energy difference delta E changes depending on that fixed lower level. As N2 increases, you notice the spectral lines get closer together, converging at the series limit. This happens because energy levels bunch up at higher N values, getting closer and closer. For instance, jumping from 20 to infinity requires the smallest energy difference of all. This pattern is a beautiful confirmation of the quantized nature of energy levels and the correctness of Bohr's postulates. It's like climbing a ladder where the rungs get closer near the top, eventually leading to freedom. Now, you might be wondering, why are some spectral lines brighter than others? Well, not all electronic transitions are created equally. The intensity of a spectral line depends on the probability of that transition occurring. Some jumps happen more often because of selection rules, kind of like traffic laws for electrons, deciding which transitions are allowed or forbidden. Also, the more electrons packed into higher energy levels, the greater the chance they'll drop down and emit photons when excited, like a crowded stadium ready to burst into a wave. This population depends on conditions like temperature or electric current. To understand transition probabilities deeply, physicists use something called dipole matrix elements, fancy math involving the overlap of initial and final electron wave functions with the position operator. The probability amplitude is proportional to the square of this dipole matrix element. On top of that, atoms sometimes have degenerate energy levels, meaning different states share the same energy. These degeneracies can increase the number of possible transitions, affecting the observed intensity and complexity of spectra. So spectral lines not only tell us about energy levels but also how electrons behave and distribute themselves quantum mechanically. Let's wrap up what we learned about atomic spectra. The energy levels in hydrogen are given by the formula. Energy E sub n is negative 13.6 electron volts divided by n squared, capturing the quantized nature of atomic energies. The wavelengths of spectral lines follow the Rydberg formula, where 1 divided by lambda equals the Rydberg constant a sub h multiplied by open bracket 1 over n1 squared minus 1 over n2 squared close bracket. The energy difference delta E between levels equals Planck's constant h multiplied by the frequency nu, making photons that shine at specific wavelengths lambda equals speed of light c divided by frequency nu. These spectral lines result from electrons transitioning between discrete energy levels, painting unique patterns for each element. Remember, the spectral series belong to different electromagnetic zones: Lyman in ultraviolet, Balmer in visible light, and Paschen in infrared, showcasing the full range of emission. And finally, the intensity of these lines depends on transition probabilities and how electrons are distributed across energy states. From fireworks to neon lights, from lasers to stars, atomic spectra illuminate our understanding of the microscopic world. That is it for today's concept. Physics is fun when you can laugh and learn. See you in the next session.